Hello. In this unit, we'll discuss structural concrete design in the context of gravity or dead man anchors. First, we'll use ACI 318-11 or the 2011 version of the ACI 318 in case you're using a different version of the code and need to know which numbers we're using. We'll use chapters 7 through 10 to guide a lecture on placing and detailing of the reinforcement, general considerations for analysis and design, strength and serviceability requirements. Then, we'll use the code to guide additional stability checks performed in this section from chapters 10, 11, and 22, which will be flexural capacity of the reinforced concrete section under full cable forces, shear capacity of the reinforced concrete section under full cable forces, and cable bearing on structural concrete. In another lecture, we'll talk about this in the context of the early strength of the concrete, and we'll adjust our compressive strength of concrete accordingly. Now, in the following diagrams, we'll estimate the beam section formed by the largest rectangle you can draw perpendicular to the loading. And that's shown here. W effective is the section width, D effective is the section depth, capital H is and B1 are from before, those are the anchor height and the width at the top of the anchor, and gamma is the actual offset of the rectangle so that we can translate those forces or some of those forces perpendicular to that rectangular section. The forces on the beam will be approximated as a simply supported beam, and the cable forces can be resolved into a distributed load. This is a conservative estimate as opposed to using fixed end conditions. So we can see the equations here, and I've also drawn diagrams for you here, the moment diagrams for a fixed and a simply supported beam. You can see how there is this area for a fixed end condition that reduces the maximum moment. So we'll use that simply supported beam moment to calculate the maximum moment. Load combinations, strength, and serviceability design will be discussed later. But first I want to address what about ramp fill. And I've added in a diagram here to explain, due to the unknown difference in stiffness between the ramp walls and the ramp fill, which was discussed in the previous sections on where we dove into the ramp wall design more, we don't want to assume that the load transfers evenly across the surface. So we'll perform the analysis assuming that the ramp fill does not contribute in both flexure and shear, but support from flexure and shear can be added later if you find that these checks are not passing.